All right, guys, we're going to move on to section 6.2, transforming and combining random variables. So a few chapters back, I think we did an example where, we had a dot plot. I forget what it was of, but had something like that. And I think it was like scores on a test. And we talked about what happens if I add 10 points to everybody's score. Well, it just takes this and it shifts it 10 units to the right. But if I did that, like if the old mean on a test was 70 and I added 10 points to everybody's score, the new mean would be 80. Okay? But since all of these points are the same amount of space away from each other, if the old standard deviation was 5, for instance, the standard deviation would not change. It would not change the spread. All right. But if I took that, so this was the effect of adding 10 to everyone's score. All right. So the mean changes. All right, but the standard deviation stays the same. All right, now if I took that distribution and I multiplied, all right, if I multiplied times 1.10, then this distribution would be more spread out. All right, so here you would have to take the old mean, which was 70, and the new mean would be 10% more than that, so it would be 77. And if the old standard deviation was 5, the new standard deviation would be 10% more than that. It would be 5.5. So here, both the standard deviation and the mean changes when you multiply by a number. But when you add a number, the mean changes, but the standard deviation does not. Now we're going to do the same type of thing, but we're talking about this in the context of random variables. Okay, so here's what happens. Let's just read through some of this, some of the notes here. So if you multiply or divide by a certain constant b, it's going to change the measure of center. Okay, just like it did here. Okay. It's also going to multiply or divide the measure of spread. So this would be 5 times 1.1. All right, it doesn't change the general shape. If something originally is skewed right, the new one's going to be skewed right as well. All right, but there's another bullet here. If asked for a new variance, you must get the new standard deviation first, then square the new standard deviation to find the variance. Okay, we'll do examples of that. Now, what about if you simply just add a number? Okay, like this top part, if you just add a number. All right, if you just add a number to a random variable, all right, it's going to add to the mean, but it's not going to change the standard deviation. So everything we said before still is in play. All right, and then the bullets down here says if y equals a plus bx is a linear transformation of the random variable x, then the probability distribution has the same shape. Here's how we find the new mean. Here's how we find the new standard deviation. And these rules apply to both continuous and random variables. So let's read the first example because the best way to understand this is to do an example. So it says one brand of bathtub comes with a dial to set the water temperature. When the baby safe setting is selected and the tub is filled, the temperature X of the water follows a normal distribution with a mean of 34 degrees Celsius and a standard deviation of 2 degrees Celsius. All right, so here it tells me X is normally distributed with a mean of 34 and a standard deviation of 2. So there's mu, there's sigma. We could also write mu of X equals 34, sigma of X equals 2. And these are both in degrees Celsius or degrees centigrade. All right, so part A, draw and label the distribution of X. So it tells me it's normal. All right, so I'm going to draw a normal curve. All right. right, we're going to put the mean down the center. So 34 degrees Celsius. This is the variable x. Tells me that the standard deviation tells me sigma is 2 degrees. And I'm going to tell the reader x is normally distributed with mean of 34, standard deviation of 2. So I've drawn and labeled the distribution of x, where x equals the temperature of water when the baby safe setting is applied. All right, so that's part A. So part B. It says define the random variable y to be the water temperature in degrees Fahrenheit instead of Celsius. Recall that to convert the Fahrenheit, you take 9/5 times Celsius plus 32. All right, so here in part B, y is the temperature of the water when baby safe setting is applied. I should say in degrees Fahrenheit, because this one was in degrees Celsius. All right. So it's asking me to find the mean and the standard deviation of y. So I'm trying to find mu sub y and sigma sub y. All right, so here's how I'm going to do it. First thing I need to do is get an equation for y. Y is the temperature in degrees Fahrenheit. So how do you do that? Well, you take 9/5 of the temperature in degrees Celsius. Well, the temperature in degrees Celsius is x. All right, and then you add 32. So this is a linear expression going from x to y. All right. Now, how am I going to find the new mean? All right. Well, if you look up here, all right, if you multiply by a constant b, so here I'm multiplying x by 9/5, that's also going to change the mean here. So we're going to take 9/5 times the old mean, which we're calling mu sub x. Okay. And what about this 32? What does adding do to it? All right. When we add or subtract, we also have to add that number to the center, which would mean I would have to add it for the mean. All right. Plus 32. So we can actually figure this out. 9/5 times what was the mean of x? It was 34. All right, plus 32. All right, so 9/5 is 1.8 as a decimal times 34 plus 32. All right, so mu sub y, I'm going to do that in the calculator, 1.8 times 34, that's 61.2 plus 32. So the mean of y would be 93.2. So when we're trying to find the new mean, we got to multiply by the coefficient and add the number. All right, and this would be measured in degrees Fahrenheit. Now, so we got the mu sub y. Now we have to find sigma sub y. So when I find sigma sub y, the standard deviation of y, the only thing that affects that is multiplying. 32 does not affect the spread. Only the 9/5 does. All right, so I have to take 9/5 times the old standard deviation. So here I would do 9/5, what was sigma sub x? Well, that was 2 degrees Celsius. All right, so this is 1.8 times 2. And 1.8 times 2 is 3.6. And this would also be measured in degrees Fahrenheit. So the old center was 34, the new in degrees Celsius. That's equal to 93.2 degrees Fahrenheit. But the old spread was 2 degrees Celsius. The new spread is 3.6 degrees Fahrenheit. Okay? Because adding a number just shifts this curve. All right, so it's not going to change the spread. The 32 does not change the spread. All right. So that's part B. Now it says draw the distribution. All right, so how would I draw the distribution? Well, okay, it's going to be normal as well, because when we add or we multiply, it doesn't change the general shape. So if x was normally distributed, guess what? Y is also normally distributed. Okay. Now, its center was 34 before. The new center is 93.2. Okay. The new center is 93.2. Okay. The old spread was 2. The new spread is 3.6. So the new spread is 3.6. So that's the new spread. That's the new sigma. So y will also be normally distributed. It doesn't change the shape. It does not change the general shape. All right, so part C. It says, according to Babies R Us, the temperature of a baby's bathwater should be between 90 degrees Fahrenheit and 100 degrees Fahrenheit. Find the probability that the water temperature on a randomly selected day when the baby safe setting is used meets the Babies R Us recommendation. Show your work. So this is given to me in degrees Fahrenheit. All right. So when I'm using the baby safe setting, here's my distribution of water temperatures in degrees Fahrenheit. So I should be using this one right here. So to do part C, I need to redraw that y distribution. I'm going to redraw the y distribution. So the center here is 93.2. All right, and y is normally distributed with 93.2 as a mean and 3.6 as a sigma. They want to know what's the probability that if I use Baby Safe, I'll get a value between 90 and 100. All right. So 90 might be about right there. All right, it's going to be less than 93.2, and 100 might be maybe about right there on the curve. So what I'm really asked to find, I'm trying to find this area. I'm trying to find that area of the y curve. So what I'm really trying to do here, I'm trying to find the probability that y is between 90 and 100. That's what the question's asking me to do. Find the probability that y is between 90 and 100. Well, we can do that in our calculator, or we could convert these to z-scores. That's the nasty way to do it. So I'm just going to go under my distributions menu, go to normal CDF. The lower bound is 90. The upper bound is 100. The mean of the y distribution is 93.2. Okay, and the standard deviation is 3.6. Paste it, hit enter, there we go. 78.35%. 0.7835. All right, what does that mean? 78.35% of the time, the Baby Safe setting meets Babies R Us recommendation. All right. 78.35% of the time, the baby safe setting meets the recommendation of Babies R Us. Okay. So that's how we do it. So what did we do here? We started with an X distribution and we transformed it into a Y distribution. And the question they were asking me to do is calculate a probability of this continuous random variable, okay, using a normal curve. That's what we were asked to do. So that was transforming. That was transforming data. We can also combine random variables. So under this it says many interesting statistics problems require us to combine 2 or more random variables. And those variables could be random or continuous, or excuse me, discrete random variables or continuous random variables. So to find a mean of a combined variable. So let's say that you have 2 random variables, call them X and Y, and we want to combine those. Let's say we have some sort of total function where total is X plus Y. All right. Well, to find the mean of the combined variable, which we would call mu of t, we would just have to take the mu of x plus the mu of y. Okay? Now, if this was a minus instead, or if you wanted to do some sort of difference, then instead of this being a plus, then it would just be a minus. Okay, that's why we did kind of 2 at once. All right. So what this formula says, to find the mean of the combination, that's what this part is, sum or find the difference of the means of the individual random variables. Okay. Now there is an important note here. When we're doing a total, when we're finding the mean of a combination, the variables do not need to be independent. Okay? They don't need to be independent to find the new mean. All right. Now, how do you find the new spread or the new variance? Okay. Well, to do this, the 2 random variables do need to be independent. If they're not independent, you cannot calculate it. All right. What this says is to find the combined variance, you have to add the individual variances. Okay. This is always a plus. See this sign? It's always a plus. You never subtract variances. You always sum variances. So you add variances. You do not add standard deviations. If they asked you for the new or the combined standard deviation, after you found this thing, you would just have to take the square root of this to find the new standard deviation. Okay. It's always summed. New variance is always summed. All right. And also what's important here is when we combine 2 normally distributed variables, the result is a distribution that is also normally distributed. Okay, so let's look at this exercise. It says a college uses SAT scores as one criterion for admission. Experience has shown that the distribution of SAT scores among its entire population of applicants is such that, all right, so we have some information about math, which they're calling the random variable x. Well, math has that. This average student has a mean of 519 on their SAT math. And they have a standard deviation of 115 on their SAT math. All right, and the critical reading, we're calling that variable y. The mean of the critical reading score is 507, and the spread, or the standard deviation, is 111. So, they want to know what the total score is. Okay, it says, what are the mean and the standard deviation of the total score? So in the old days when people took the SAT, they had these two components. So to find their total score, all you would do is add these two means together. All right, so to find the mean of the total score, we would just take the mean of the math score plus the mean of the critical reading score. So this is going to be really easy to find. Mu of x is 519. Mu of y is 507. So if I add those together, we get 1,000, what's that, 26. All right. Remember, to find the new mean, we don't even have to worry about if these are independent. Now, to find sigma sub t, okay, to find sigma sub t, we would take the square root of the variance of t. All right. However, we cannot find this. Here's why. In this case, x and y, these two variables are not independent. Let's think about why they're not independent. People who usually do well on the math section also do well on the critical reading. So since individuals take this, if they do well, just knowing about students, if a student does well in the first section, they're more likely to do well. So there's some dependence between these two variables. Okay, there's some dependence on it. So since x and y are not independent, standard deviation of the combination cannot be found. It can be found, but it's above our level to find it. Okay, we have to use something. We would have to use something called an ANOVA to actually help us with that. But for our purposes, we don't have the tools to find that. Okay, so to use these formulas, they have to be independent, and they're not. Okay, so we cannot do that. So we cannot find the variance, so we cannot find the standard deviation. So let's look at another exercise here. It says a large auto dealership keeps track of sales and lease agreements made during each hour of the day. Let x equal the number of cars sold and let y equal the number of cars leased. All right, so here x equals the number of cars sold and y equals the number of cars leased. During the first hour of business on a randomly selected Friday. So I have some information about cars sold and the probabilities during the first hour on a randomly selected Friday. And I have information about cars leased and their probabilities. Okay. Based on previous records, the probability distributions, of x and y are as follows. So how can we find the mean number of cars sold and the standard deviation of the number of cars sold? Well, we can use our calculator. All right, if you remember how to do this, let's just go under one of our lists. All right, and let's put the number of cars sold in list 1, 0, 1, 2, 3, and let's put their probabilities into list 2. So 0.3, 0.4, 0.2, 0.1. These numbers better add up to 1, and they do, to make it a valid probability distribution. So if you remember here, if we go stat over to calculate one variable stats, list L1, frequency list L2, and calculate, it's going to give me the average. So the average number of cars sold is 1.1. And it's also, this number right here is the standard deviation, 0.9434. We'll just round to 3 places. 0.9434. Now, let's do the same thing with the number of cars leased. Let's find the mean number of cars leased and the standard deviation of number of cars leased. So I'm going to go under my list here, stat edit. Okay. Well, we don't have a 3. Okay, we only have 0, 1, and 2, and the probability of 0 cars being leased is 0.4, the probability of 1 car being leased is 0.5, probability of 2 cars being leased is 0.1. Okay, and those numbers add up to 1, which is good. Let's do the same thing again. Let's find the one variable statistics for list 1 with frequencies L2. Okay, so there, 0.7 cars on average get leased. All right, and the spread is 0.6403. Okay, let's just start thinking about if these things are independent. Well, if someone buys a car, they're not going to lease a car at the same time. So just thinking about these things are probably independent. These variables are probably independent. People who lease cars, generally businesses that can write it off as a tax expense sometimes, or people that want a cheaper payment. People who want to own a car go for buying a car rather than leasing a car. So now we're going to have a new variable, which we're going to call D. Define D to be the difference in the number of cars sold and leased. Okay. So it gives me some sort of linear combination. D equals the number of cars sold minus the number of cars leased. So part A, find and interpret mu of D, okay, the mean of the difference, and the standard deviation of the difference. All right, so let's do that. So to find mu of D, okay, I would just take mu of X minus mu of Y, because it's going to follow that same sign. All right. So in this case, mu of D would equal, on average, 1.1 cars get sold. On average, 7/10 of a car gets leased. So if I subtract those, I get 0.4. So what is the meaning of that? Okay, the mean difference, okay, on average, 0.4 more cars get sold than leased on the first hour of business on a Friday. All right. Now it's also asking me to find sigma sub D, the standard deviation of the difference. All right. Before I can find that, I have to find the variance. So how am I going to do that? Well, I have to take the variance from X, and it's always plus. It's always plus. Even if this is a minus, that's always a plus. We always add variances. Okay. So to figure out what sigma sub D would equal, you would have to take the square root of both sides. You'd have to take the square root of both sides. So that would be sigma x squared plus sigma y squared. Okay, don't try to break these up individually. You know, you're not allowed to do that. All right, so how do we do that? Sigma sub D. Well, what was sigma sub x? Sigma sub x was 0.9434, but that was a standard deviation. Here I need a variance. So I need to take that 0.9434 and I need to square it to make it into a variance. And then I need to add the variance of y. Well, how do I find the variance of y? Well, the standard deviation of y was 0.6403, so to make that into a variance, I have to square it. Okay. So I can actually do this in one step. My calculator. So take a square root and just type in 0.9434 squared plus 0.6403 squared. And there we go. 1.1402. All right. and the units here would be cars. So the mean of the difference, on average, there's a difference of 0.4, okay, but there's a huge spread. Okay? There's a much bigger spread, all right? So sometimes, you know, and sometimes 2 cars get leased and no cars get sold, all right? So that difference would be 2. Sometimes if it's 2 and 1, it would be 1. All right, if both of them were 2, then the difference would be 0. Sometimes it would be -1. All right, and then you could do it with all 3 numbers. So looking at all the combinations on average, this is how the difference deviates on average. Okay. So that's part A. Part B. It says the dealership's manager receives a $500 bonus for each car sold. Therefore, S equals 500x. Find and interpret the mean and standard deviation of the bonus that the manager receives from the sale of vehicles on the first hour of business on Friday. Okay. So here they tell us in part B that S equals 500x. So what they want me to do is they want me to find mu of S. And what's the mean amount of bonus from sales? Well, when you're multiplying x by 500, that's also going to affect the mean by 500. So we're going to take 500 times mu of x. Okay. So we're going to take 500. Mu of x is 1.1. Let's see, that would be 550. Okay. So that's mu of s. That's how much bonus on average the manager receives from selling cars. Now what about sigma s? Define sigma s. All right, well, when we're multiplying, that also changes the standard deviation by that number. So we would have 500 times sigma x. So sigma s would equal 500 times 0.9434. Which turns out to be $471.70. So there's a lot of spread. There's a lot of spread there. All right. Now, part C says the dealership's manager receives a $300 bonus for each car leased. Therefore, L equals 300 times Y. Find and interpret the mean and standard deviation of bonus that the manager receives from the lease of vehicles. So I'm trying to find mu of L, and I'm going to try to find sigma of L. Well, same way as before, we would take 300 times mu of Y there, and here we would take 300 times sigma sub Y. So this would be 300 times 0.7, which turns out to be 70% of 30 is 210. So mu of L is 210. And over here, we would take 300 times 0.6403, which is approximately about $192.09. All right. So on average, this is the bonus that the manager gets for leasing cars, but there's quite an amount of spread. Okay, it doesn't always get that. Sometimes it's less than that. Sometimes it's more than that. So we've done part A, we've done part B, we've done part C. Now, it's asking me, find the mean and standard deviation of the difference in bonus amounts. Find the mean and the standard deviation of the difference in the bonus amounts from selling and from leasing. So how are we going to do that? I'm actually going to do that on the previous sheet of paper. I'm just going to do it on the back. Actually, I'm going to do it on another sheet of paper. All right. So they defined a new variable in part D. Okay. They defined this new variable for me. So in part D, the difference in bonuses equals the bonus that the manager gets from selling minus, S minus L. All right, I made a mistake here. This should be S minus L when I was typing out the note card. So we're trying to find mu of B and sigma of B. So let's write our equations for that. So how are we going to find the difference in the bonus amounts? Well, to find the mean, it'll be mu of S minus mu of L. It's going to follow that sign. But to find sigma sub B, you can't find sigma first. You have to use variance. Okay? And you can only do that if these two variables are independent, which we assume they are. Okay, so we would have to take sigma S squared. We'd have to take the variance of S and the variance of L, but we never subtract. Even if this is a minus, this always is a plus. So if I want to find sigma sub B, I got to take the square root of both sides. All right, so sigma sub B would equal sigma sub S squared plus sigma sub L squared. So at this stage, we're just going to plug in numbers. It's not going to be that bad. All right, so mu of B equals mu of S. What's mu of S? $550. It's what the manager expects to make from bonus the manager expects to receive from selling cars, minus mu of L, which is this number right here, 210. All right, so if I do that, 550 minus 210, I think that's $340. So on average, what does this mean? What's the meaning of that? On average, the manager receives, on average, $340 more in bonuses from selling than leasing. That's how much more he gets from selling than leasing. But that doesn't happen every time. There's some spread in that distribution of that variable. Right. What was the spread of the bonus that he gets from selling? That was $471.70. That's a standard deviation. You got to turn it into a variance, so you have to square it. Plus, what was the spread of the bonus he gets from leasing? That's 192.09. So 192.09. But that's a standard deviation. You got to turn it into a variance. Again, you can do that in one step in your calculator. So big square root, 471.70 squared plus 192.09 squared. So when you do that and round it to two places, you get a standard deviation of about 509.31. Okay. So this is what the manager expects to get on average, but that can deviate. On average, the amount deviates $509. Okay. So it could go down quite a bit, it could go up quite a bit. So some days he's going to make more from leasing. Some days he's going to make a lot more than that from selling. Okay? So that's how you kind of walk through the process of combining these random variables. Let's look at another problem here. So it says the diameter, C, of a randomly selected large drink cup at a fast food restaurant follows a normal distribution. Okay, so let's just kind of highlight some important pieces of information here. So on the cup itself, the cup diameter, okay, so like if we have a cup, all right, here's my cup, all right, so this diameter across the top of the cup is C. Okay. So C follows a normal distribution with a mean of 3.96 inches and a standard deviation of 0.01 inch. Okay, that's the mean, that's the standard deviation. All right, since it's normal, you could draw a normal curve to represent that. All right. Now let's see, so I'm just going to kind of highlight that in red. The diameter L of a randomly selected large lid, so L is talking about the diameter of just the lid. All right, so the lid that goes on top. Okay, so there's the lid that's going to go on top of that cup. And that has a certain diameter. And that's a random variable, which we call L. All right? And it tells us this lid, the distribution of lids, also follows a normal distribution. Also follows a normal distribution. With a mean of 3.98 inches and a standard deviation of 0.02 inches. All right, so we could actually call this mu sub c and sigma sub c of the cup itself. And here's the mean of the lid and the sigma of the lid. All right, now this should make sense. To be able to fit this lid onto this cup, the lid has got to be bigger than the cup. All right. So, lid will fit on cup if what? Well, we know that L has to be greater than C. All right. In other words, if L has to be greater than C, that means that L minus C should be bigger than 0. Okay? L minus C should be bigger than 0. But if this is too big, then when you put it up to your mouth, the lid's going to fall off. All right? So it can't be more than 6/100ths of an inch. Okay? So L minus C has to be bigger than 0, but it has to be smaller than 0.06. All right. So another way we could say this is, let's define a new variable. Let's call D the difference. So let's define the difference as L minus C. Okay. So the lid will fit on the cup if the difference is smaller than 0.06 but bigger than 0. So the lid will fit on the cup if the difference is between 0 and 0.06 inches. All right. Now let's kind of read the question. It says, what is the probability that a randomly selected large lid will fit on a randomly chosen large drink cup? So we pick a cup from our stack and we pick a lid from a different stack. Okay. And the question is, what's the chances that the lid's going to fit on the cup? So what's the chances that the difference is going to be somewhere between 0 and 0.06? So how are we going to do this? What are we trying to find? And I'm going to use my other piece of paper again. All right, I'm trying to find the probability that the difference is smaller than 0.06 but bigger than 0. That's what the question's asking for. So to be able to answer that question, if this is my difference curve, if I call this my difference curve, all right, what's the probability that I get something between 0 and 0.06? So I need to find information about this difference curve. All right, so let's kind of go back to what the problem told me. I know that I defined my difference as the size of the lid minus the size of the cup. Okay, so to find the mean difference, we would take the mean lid diameter minus the mean cup diameter. So what was mu sub L? Okay. Mu sub L was 3.98. Okay, what was mu sub C? It was 3.96. So this is 3.98 minus 3.96. So that would be 0.02. So 0.02 is the mean difference. So on average, a lid is 2/100ths more than the diameter of the cup. Okay. So we figured that out. All right. And by the way, how do I know that D will be normal? Well, the cup sizes, right, the cup sizes were normal and the lid sizes were normally distributed. So when we combine these two variables, okay, since both of these are normal, D also has to be normal. So D is automatically normal, okay, because these two were normal. Okay. So we found where the center of the difference distribution was. All right, that's 0.02. Now, are these two things independent? Yep, you take a lid out of a stack of lids and you take a cup from a stack of cups. They have no impact on each other. Okay, they have no impact on each other. You know, one being really big and one being really small has nothing to do with each other. These variables are independent. So as long as they're independent, we can figure out what the standard deviation is. So before I do that, before I can find sigma sub D, I need to find variances. Remember, you can only add variances. So I need to take sigma sub L squared, that's the variance of the lid diameters, plus the variance of the cup diameters. So if I want to cancel out this square, then I have to take a square root. So to find sigma sub D, we're going to take sigma sub L and then square it. Well, sigma sub L is 0.02. So we're going to take 0.02 and square it. Sigma sub C is 0.01. And we're going to square it. All right. So I'm going to do that in my calculator. 0.02 squared plus 0.01 squared, all underneath the square root. And that's 0.02236. I'm just going to use 4 significant figures. All right, so that's the spread of this distribution. So if I go over one standard deviation, here's the sigma. Sigma is 0.02236. And I'm just going to store this temporarily in my calculator. I'm going to say that's A. So I keep all the decimals. Okay. So 0.02236. All right, well, what are we trying to find? We're trying to find the probability that the difference is from 0 to 0.06. Well, where is 0 on this curve? Well, 0 would fall to the left of the mean. So maybe about, I don't know, right here. That's where 0 is. Because remember, this is the difference distribution. And where is 0.06? Well, 0.06 would be to the right, almost 2 standard deviations out. So what I'm actually trying to do here is I am trying to figure out what the area of this curve, under this curve is. All right. So here's how I'm going to do it on the calculator. This is a normal curve. So I'm going to go to my normal CDF. What's the lower boundary? 0. What's the upper boundary? 0.06. Okay, what's the mean of this distribution? It's 0.02. What's the standard deviation? Remember, I stored that as A. Again, here, that's why I stored it, so I keep all the decimals. Okay, so again, 0 to 0.06, 0.02, A. Hit enter, paste, and there we go. The probability that the difference is between 0 and 0.06 equals, according to my calculator, 0.7776. Let's interpret this. There is a 77.76% chance that the lid will properly fit onto the cup. Okay, so I pick a lid at random, I pick a cup at random. Okay, I have a little bit better than 3 and 4 shot of the lid fitting. If it's too big, it can't be bigger than 0.06. So that's what the properly fit means. All right, the lid can't be smaller because if the lid's smaller, then it's not going to go over the cup. All right. Now, if they're exactly the same size, you'll probably be able to squeeze it. So a difference of 0 means they're exactly the same size. Okay. So that's how we do that problem. All right. So kind of just backtracking just a little bit. This problem up here was about combining discrete random variables. These are each discrete random variables. This example here is about combining continuous variables. Okay, so it's done the same way. Okay, it's done the same way with the same types of calculations. So that's the important point there. All right, so hopefully that made sense. You might have to watch this a couple times to get really comfortable with combining and transforming discrete and continuous random variables. But I appreciate you watching.